There are plenty of theorems in math that are very easy to use, but extremely hard to prove. Today, I would like to give you guys a small taste of that. Let's take a look at this question right here first. Suppose we want to calculate the limit as x approaching 3 of x times the square root of x plus 1. Well, how do we do it? It's not bad at all, right? Because we can simply put a 3 into this x, and then we get 3 times the square root of 3 plus 1. Work this out, we get 6. Done. But what makes this okay? In fact, we use the limit law for product, which says because inside here we have two functions multiplying, so we first look at the limit as x approaching 3 of the first function, which is x. Does this exist? Yes, the answer for this right here is 3. Then we look at the limit as x approaching 3 of the second function, which is the square root of x plus 1. Does this exist? Yes, the answer for that is 2. Then the limit law says we can just simply multiply them together, and that's exactly how we got the 6. Good. Now, the question is, how do we prove this? Well, this is the limit, therefore we will have to use the epsilon-delta definition for limit. And in fact, today we'll do the general case right here. But before that, let me just remind you guys what the epsilon-delta definition is first. So recall, if today we have the limit as x approaching some number, let's say a, of some function f of x. Let's say this right here is equal to L. This means we must have, for all epsilon greater than 0, there exists a delta greater than 0, such that right here we first look at the distance between x and a, so we just subtract them and put that inside of an absolute value. If this distance is less than delta, and right here we don't want x to be equal to a, so we want to say this absolute value is positive. If this happens, then we can conclude that the distance between the function and the limit L, and again we'll just subtract them and then put it inside of an absolute value, this distance will be less than epsilon. And we have done a lot of epsilon delta examples in the past, so go ahead and check them out, because today this video here is pretty hardcore, I will tell you guys that. Alright? Now, as you guys saw earlier, we are not just going to be proving this statement, right? Because this is just x times the square root of x plus 1. It's just for these two particular functions. No, we don't want that. Instead, we will prove the general case. And here we go. Given the limit as x approaching a f of x, let's say this is equal to L. And the limit as x approaching a g of x, let's say this is equal to m. We are going to prove that the limit as x approaching a f of x times g of x is just equal to L times m. First off, take a deep breath and just relax. Just calm down and then put on the PF. You don't get any partial credit for this, but just put on PF. It's a good start. And let me tell you, whenever we do epsilon delta definition for limits, the first line, just go ahead and put down given epsilon greater than 0. And again, you don't get any partial credit, but it's a good start. Usually for this kind of questions, don't expect to be able to finish this in one go. It usually takes at least two parts. The first part is that you're going to break down the conditions to see what are the things that we can use. And then the second part is look at the conclusion. You want to see what are the things that you want to happen. So let's actually go ahead and look at the conclusion right here. Let's take a look at what are the things that we want to happen. We already have epsilon is greater than 0. And now let me go to the next page, because it will take in at least 2 pages to do this. We already have epsilon is greater than 0. So what we need is we must choose a delta, and this delta must be greater than 0, but I don't know what it is yet. So I'll just put down equal and then just leave it. Again, just count down and just leave it like this. And then we are going to say, suppose the distance between x and a is less than delta. Again, we also want the distance to be positive. Then we want to see that the distance between our function and the limit, and let's come back here. This time the function is f of x times g of x, and then the limit result is L times n. So we will have to subtract them and put that inside of an absolute value. So we want to see f of x times g of x minus Lm instead of the absolute value. And hopefully you can see that whatever happens right here, and then at the end we'll see that this is less than epsilon. But of course, you cannot just simply put this down right here and then say, hey, go fill this out. No, you cannot do that. You have to really think about what exactly we have to go from here. So that's the idea. And perhaps let's just go ahead and think about this a little bit. If you notice this right here, it seems like we cannot do any algebra, right? Because it's just f of x times g of x minus Lm. Oh man, too bad. So in this case, maybe let's go back to our given information. Well, we see that we have this. The limit as x approaching a, f of x is equal to L. And if you go through the definition, just like this right here, you'll see that at the end, we have something like this. So I'm going to tell you, we are going to end up with the absolute value of f of x minus L is less than something, epsilon one not, all right? And then I don't know. And then this right here, absolute value of g of x minus m, this right here is going to be less than epsilon and something. Okay. So as you can see, we kind of want to work with these two expressions. But if you go back to what we have, we don't have that, right? But it's okay, because if we don't have it, let's produce it. Here is how we can do it. Here, we have f of x times g of x. And then at the end here, let me just put down minus Lm. Well, I really want to see f of x and then minus L. So maybe I will just go ahead and say I want to subtract L here somehow. But of course, if I just put that, it's going to change the whole thing. So I will have to just add L. So that, you know, minus L plus L doesn't change anything. If you look at the second part, that's pretty good because we can factor out the L. However, for the first part, it seems that there's nothing we can factor. But since here we have the g of x, why don't we multiply the L with g of x as well? Let's go ahead and try that. So far so good, and now let's do some algebra. Right here, as we can see, we can factor out the g of x from the first part. So let's go ahead and do that. So we have g of x times f of x minus L. And then this right here is still instead of an absolute value right here. And then we add. For the second part here, we can factor out the L. So we will have the L here, and then times g of x minus m. And that's actually really good because here we have the f of x minus L. Likewise, here we have the g of x minus m. And those are the things that we were talking about earlier. That's pretty good. Now, pay attention to this right here. For the first part, we have g of x times this quantity, and then plus L times this quantity instead of an absolute value. We are going to break it apart. And we can do so by using the so-called triangle inequality. And let me just break it down for you guys, and I'll tell you guys what exactly that is. We can say this is less than or equal to the absolute value of the first part, which is this. So I will just write down g of x times f of x minus L. And then we add absolute value of the second part, L times g of x minus m. Again, the first part, you put that instead of absolute value, and then the second part, you put that instead of another absolute value, and you see that this right here is the less than or equal to. And I will just remind you guys, this is the triangle inequality, and it says the following. So I will also record this right here. This is the triangle inequality, which says if you have absolute value of two things adding, let's say a plus b, this right here is always going to be less than or equal to absolute value of the first plus the absolute value of the second. And of course, you can just plug in some values for a and b and try it out. Or the reason that this is called the triangle inequality is because if you draw a triangle, it's much more clear. And I'm going to leave that to you guys. All right, that's what we have. And now, have a look. We have two things multiplying inside right here, right? let's use the property of the absolute value, which says that we can just take the absolute value of the first and then multiply the absolute value of the second. So this is equal to what I'm about to write down, which is the absolute value of the first, that's g of x, and then multiply by the absolute value of the second, which is f of x minus L. And then we have absolute value of L times absolute value of g of x minus m. Good, very good. Why? Because this right here is exactly what we were talking about earlier here. Likewise, this is what we are talking about right here, right? That's good. Now what though? It seems that we still don't have anything to work with. But it's okay, just calm down a little bit. Remember, what did we talk about earlier? We wanted to have like all these things at the end to be less than epsilon, right? And now we have two parts. Here is the first and this is the second. So wouldn't it be nice if we can somehow make the first part somewhat epsilon over 2 and then the other part also epsilon over 2, because when we add them up, we get epsilon. So that will be very nice. Okay. Alright, that looks pretty good, but we have to really think. Perhaps let's start with this part. Why? Because absolute value of L is just a constant. It's easier. If you look at absolute value of g of x, that's still a function, so I don't want to deal with that yet. Let's just focus on the absolute value of g of x minus m. So what can we say about this? Now let's go back to this page, and we are going to use this condition here. So here we go. I'm going to start by saying, since we know the limit as x approaching a of g of x, this right here is equal to m. So we can use the epsilon-delta definition to write down the whole thing from earlier here. And hopefully we have some inequalities that we can use. But before that, we will have to have an epsilon. Are we going to just use the epsilon? Well, let's see. Since we have this limit, and we already have the epsilon, which is, of course, given to be greater than 0. And you will see why I put this down right here like this. So now we have these two things. So we know that there is a delta, but you know we have other limits coming up, right? So I'm just going to call this delta 1 greater than 0. And because this limit exists, this delta 1 must exist already. And then later on for other limits, I'll use delta 2 or whatnot. Okay, so there's a delta 1 greater than 0 such that when the absolute value of x minus a is less than delta, and we want to make this positive, then we get, so this implies the absolute value of the function, which is g of x minus m, is less than what I put down right here, which is just epsilon. Does this do us any good? Let's go back to here. You see, right here, I'm saying g of x minus m in the absolute value. Earlier, I have it less than epsilon, but this is going to be messed up because at the very end, I really want to just end up with an epsilon. But if I put down epsilon right here already, then what do we do, right? Let's see. Right here, this is absolute value of L, and again, it's just going to be a number. So maybe we should just divide this by absolute value of L. Can we? So that this and that cancel. It looks good, right? And of course, you can go back to the previous page right here. And then maybe we can just write this as, we want this to be less than epsilon over the absolute value of L. It looks good, but there is a problem for this. Let's go back here. Do you notice what the problem is? What if absolute value of L is equal to 0? Then is this expression legitimate? Unfortunately not. Oh my god, this is horrible. But don't worry. Don't worry, alright? Don't worry. Just in case that the absolute value of L is equal to 0, well, don't worry. Let's just add 1 to it. Why? Because this is never going to be equal to 0 anymore, right? And in fact, if you have this expression, you can still say this is less than epsilon over absolute value of L. That is true because here the denominator is bigger. So this is still going to work, and we still have a very nice inequality that we can use later on. So that looks good. However, there's one small thing. Remember earlier we said that we want this part to be somewhat epsilon over 2? Well, with that being said, let me actually multiply a 2 right here as well. So this part is what exactly we want to have. Well, we can just go back here and then write that down. So we don't just want epsilon. We want to write epsilon over 2 times the absolute value of L and then plus 1. And this is insanely crazy. I know, because like, wow, how do we come with this? And the truth is, maybe you can end up with a different expression and still make it work. That's what makes this kind of things really hard, because this is not the only way to do the proof. But we do want to say that this expression is indeed positive, because absolute value of L is never negative, and then plus 1 is always positive, and then all the rest is positive. So this statement is legitimate. So we have this thing right now. We can just come here and then write that. So 2 times absolute value of L plus 1. And now we can legitimately put that expression right here. So this thing checks. Very, very nice. And of course, later on, we just have to multiply with absolute value of L. And I'm just going to take care of that later. Now, let's probably do the same thing for the absolute value of L, absolute value of f of x minus L. Do we also want epsilon over something? Here's a small problem. This right here is absolute value of g of x. It's a function. So if you say absolute value of g of x on the bottom, this is not a constant, so you cannot just divide it by that. So no good. In fact, we will have to somehow get a bound right here first. And how can we do that though? Absolute value of g of x. How can we set an upper bound so that we can just say this is less than or equal to something? Well, let's go back to here again. Make sure that we utilize all the given information to the full extent. So we still want to have g of x somehow, so maybe this kind of expression. Oh man. And this time I just want to end up with a number maybe. So how can we do it? Well, I'm going to write down something extremely obvious. Notice, I'm going to write down 1 is greater than 0. Why? Because this one acts as a epsilon. Alright? 1 is certainly greater than 0. And then you can just put down 1 is greater than 0. And then you can kind of repeat the same thing right here. And at the end, just write down this less than 1. And that's legitimate. And if you guys have done the epsilon-delta definition for quadratic function situation, you see that we have used 1 many times before as well. But anyway though, notice that 1 is greater than 0. So we know that there is another delta. I'm just going to say that's delta 2 is greater than 0, such that when the absolute value of x minus a is less than delta 2, and just notice that this right here should have been a delta 1. Sorry about that. But anyway though, this right here, if it's less than delta 2 and in the meantime it's positive, then we must have the absolute value of g of x minus m is less than 1. Again, this one right here acts like the epsilon. So of course this is legitimate. And let me just erase this because that's not really like the epsilon that we have. Good. Now what though? Here's the thing. Earlier we were talking about we just want a bound for the absolute value of g of x. We don't want to have this, right? So let's just make some observation and see what we can do with absolute value of g of x. First, we see the absolute value of g of x. What can we do? Well, we have this, so we can use. And the inside is that we have the minus m, so we do this. This right here is the same as absolute value of g of x, and then let me really have the minus m. But of course, this will change the whole thing. But don't worry, let's just add the m back. So this is still the same as what we have earlier. Now have a look. This plus that inside of the absolute value. Yes, we can use the triangle inequality again. So this right here will be less than or equal to absolute value of the first part, which is g of x minus m, and then we add it with absolute value of m. Perfect. Now what can we do? Well, we know that the absolute value of g of x minus m is less than 1. So we'll just say this is less than 1, and then plus absolute value of m. Wow! So have a look right here, people. Absolute value of g of x is less than 1 plus absolute value of m. And now this is just a constant. So we can go back here, and then we can write down absolute value of g of x. Now we know we have that 1 plus absolute value of m that we are about to use. With that being done, what can we put down right here? Well, 1 plus absolute value of m is always going to be positive. So let's just go ahead and divide it by that. So we divide it by 1 plus absolute value of m. And then similar reason like earlier, let's also have the 2 on the bottom like that. So now, in order for this to happen, we will have to use the definition for the limit as x approaching a of f of x is equal to L. So I will just have to come back here and then write that statement down so we can use it. Also because, so just say also because, not because, because the limit as x approaching a f of x is equal to L. And what's the expression that we have earlier? Epsilon. Don't just put on epsilon greater than 0. We want to have this expression, right? So it's epsilon over 2 times the absolute value of m plus 1. And this expression, again, it's positive. Then we know that there is another delta, so I'm just going to put down delta 3 greater than 0, so that if the absolute value is in between of 0 and delta 3, so I'll just write down like this. Then we know that absolute value of g of f of x minus L is less than this part. So I'll just kind of squeeze this in a little bit. Just put this aside a little bit. And I'll squeeze this in, which is epsilon over 2 times the absolute value of m plus 1. And now, with this statement written down, this right here is legitimate. Yay. So now, let me just kind of read what we have so far for you guys. We have given epsilon is greater than 0. And then we came up with all these statements that we can use like 1, 2, actually 1 and then 2 and 3, right? And now, in order to finish a proof for this right here, remember we have to go through epsilon is greater than 0, and then we have to choose delta equal to what, right? Well, earlier, notice we have how many deltas? We have a total of 3 deltas already. Have a look. What do we have? Here, we have delta 1 and delta 2 right here. And then lastly, we have delta 3. And they all exist. That means we can use them. And in order for us to finish up the proof for this, in order for us to choose this delta, we are just going to pick the minimum. Because once we have this delta being the minimum of delta 1, delta 2, delta 3. When we suppose the absolute value of x minus a is less than this delta, then this implies the absolute value of x minus a is less than all delta 1, 2, and 3. So that means all the inequalities that we came up with earlier we can use. And then again, we have all this work already, so we don't have to change anything. That's perfect. Perhaps I will erase the less than epsilon because we have to work it out a little bit more legitimately. So now, let's focus on this part and then let's write it out carefully. Well, we will end up with a less than. First off, we know that this thing, right, is less than 1 plus absolute value of m. So that's good. And then let's also write down the rest. Epsilon over 2 times 1 plus absolute value of m. And then we add absolute value of L. Let's just keep it. That's absolute value of L. And then we have epsilon over 2 times absolute value of L plus 1. Now for the first part, we see that this and that cancel out precisely. So just get epsilon over 2, and that is extremely nice. And perhaps let me just write that down right here. We have epsilon over 2. Very nice. Plus, and what can we do right here? In fact, we can say this part is less than epsilon over 2 as well. And why is that? Well, again, let's just look. If we see epsilon times absolute value of L over 2 times absolute value of L plus 1, this right here we know for sure it's going to be less than epsilon times absolute value of L over 2 times. Let's just get rid of this plus 1. So we have 2 times absolute value of L, like this. And you can just think about it as like this and that cancel. But if L is equal to 0, then this might not be too legitimate. But I can tell you this right here is for sure less than absolute. This right here is for sure less than epsilon over 2. That's for sure. And I just don't want to have the cancel the 0 over 0 case on my proof. So let me just erase this, and hopefully your reader or your professor or your teacher or anybody who's reading your proof is not so picky, and they can see that this is indeed true. All right, so that should be cool. Okay, that's pretty clear. All right, ladies and gentlemen, what did we end up with? Epsilon over 2 plus epsilon over 2. Of course, that is just equal to epsilon. So what do we do? As you can see, what do we have? Given epsilon greater than 0, we got delta right here, and of course this right here for sure will be greater than 0 because everybody was greater than 0. And then suppose that if the absolute value of x minus a is less than delta and also positive, then we see that this expression is less than epsilon. That means with the epsilon delta definition, we finish the proof, and you don't put the box around epsilon. Don't do that. That's extremely horrible. Don't do that. What you put is, you put a box right here and shade this in. Oh, this feels so good.